doing is L identifies the sublevel the outer electron is in. So, let's look at principal energy level number 1. Okay, to come up with L, L is going to equal n minus 1. Well, we are in n is equal to 1, so 1 minus 1 equals 0. This is L if we're in PEL number 1. Okay. Now, 0 is telling, if you have a 0, that's telling me that it's an S sublevel. 0, if you do this formula and get a 0, it's an S sublevel. Now, look here. PEL number 1 only has an S sublevel. Okay. So the electron has to be in an S. If we're in PEL number 2, now we have 2 sublevels. We know that this has an S and a P. So, if we look at n minus 1, we end up with 2 minus 1 equals 1. A 1, if L equals 1, it is a P sublevel. Now remember, PEL2 still has an S. So in principal energy level 2, there are 2 quantum numbers. There is L can equal 0 or L can equal 1. And it really depends on how many where the electrons are. So if the outer last electron is in the s orbital, the second quantum number would be 0. If it's in a p, the second quantum number would be 1. PEL number 3. We know that principal energy level number 3 has an S, a P, and a D. Well, which means there are 3 different L's. L could equal 0, L could equal 1, and L could equal 2. Well, if L equals 0, that tells me that it's in an s orbital. It's in the 3s orbital. If L equals 1, that tells me it's in the 3p orbital. If L equals 2, that tells me it's in the 3d orbital. All right, now remember, we're talking about where the last electron of the electron configuration is, okay, which PEL it is. So let's just kind of quick summarize here. Our second quantum number. Is L. Okay. If L is 0, it tells me that that last electron is in the s orbital. If the L is 1, that tells me that the last electron is in a p orbital. If the second quantum number is 2, that tells me that it's in a d orbital. If it's 3, that tells me that that last electron is in an f orbital. If it's a 4, it tells me that it's in a g orbital. All right. So all the second quantum number is telling me is what type of orbital the last electron is in. That's all it's telling me. And you're going to have a 0, 1, 2, 3, or 4. Okay, and it's just found by n minus 1. All right. Let's look at my third quantum number. The third quantum number tells me which orbital the electron is in. Okay. So let's write a couple things. So it's the actual area of space where we find the electron. B. So it's the orientation of the orbital we are looking at. Okay, now let me just explain. So remember, if we have a p orbital, that tells me that we have px, py, and pz. What this third quantum number is telling me is which one of these orbitals it's in. That's all it's telling me. Okay? The third quantum number tells me which orbital it's in. It's denoted m sub L. And this is the magnetic quantum number. To calculate ml, it's a range, and it goes from negative L to 0 to positive L. So remember L, let's see, L is our second quantum number. And it tells us the type of sublevel. It tells us the type of orbital. So if we have an S, L is equal to 0. So in this case, the range, ML, equals negative L to 0 to plus L. Well, negative 0 is 0. Then we have 0, and then positive 0 is also 0. So if it's an S orbital, there's only one area of space there's only one area of space. So in this case, if you're in an S orbital, ML is equal to 0. Well, what if we have P's? In P's, L is equal to 1. So now remember, ML is equal to negative L, 0, positive L. Okay, so in P's there are 3 orbitals, and they're just named -1, because that's negative L, 0, and plus L, plus 1. Now remember, all this is telling us is it has 3 orbitals. And instead of naming them X, Y, Z, we're just naming them -1, 0, +1. That's all we're doing. So this would be technically Px, Py, Pz. Okay. So our third quantum number is just identifying which of the orbitals it's in. Well, what if we have a d? Remember, the d orbitals have 5 areas of space. And for a d, L equals 2. A d orbital, L equals 2. So ML is equal to -2, -1, 0, +1, +2. These are my 5 d orbitals. We're just naming them. Okay, -2, 1, 0, +1, +2. That's all we're doing with these d orbitals. An f orbital has 7 areas of space, and L equals 3. So my third quantum number, or ML, would be equal to -3, -2, -1, 0, +1, +2, and +3. 1, 2, 3, 4, 5, 6, 7. These are my 7 areas of space. These are the 7 f orbitals. Okay, I'm just naming them. Now, the fourth quantum number. This is number 4. The fourth quantum number is denoted ms. And it's the magnetic spin. It's telling us the spin of the electron is really what it's telling me. Well, it's telling me that what it's really telling me is if the last electrons are paired or unpaired. That's what it's telling me. So let's just hold on a minute. All right, so ms can be only 2 things. It's either +1/2 or -1/2. Those are your 2 options for ms. Okay. So our magnetic spin is either +1/2 or -1/2. If there is one unpaired electron in the orbital. So if that last electron is unpaired in the orbital, the fourth quantum number, or the magnetic spin number, is +1/2. If there is 2 electrons in the orbital, or they're paired, it's going to be -1/2. Now let me show you what I mean, because it's pretty simple. If we have hydrogen, its electron configuration is 1s1. It has 1 electron in this outer orbital. Phone's ringing off the hook. Sorry about that. Back to here. So it has 1 electron in this s orbital. So the fourth quantum number, see this is unpaired. Okay, the fourth quantum number, or ms, would equal +1/2 for hydrogen. For helium, it has a 1s2 electron configuration. So it would have an up and a down. It has 2 electrons in here. So it would, in this case, the ms value would be -1/2. Okay, so let's go ahead and try this. Let's come up with our 4 quantum numbers. Okay. Do we want to do that yet? Let's do this first. Let's talk about the Pauli exclusion principle. What the Pauli exclusion principle says is that no 2 electrons can have the same exact set of 4 quantum numbers So no 2 electrons can have the same exact 4 quantum numbers in the same atom. Okay. So so what this is doing is it's giving us a roadmap to each specific electron in the atom. All right, now before we actually do this, let's summarize. Okay, so we're going to have we have 4 quantum numbers. We have n, we have L, we have ML, and we have MS. L, if you remember, is our principal energy level. Okay, and we can have n equals 1 through 7. L is our sublevel. If it is an S, L is equal to 0. If it is a P, L is equal to 1. If it's a D, L is equal to 2. If it's a F, it's a 3. And if it's a G, L is equal to 4. M sub L tells us what orbital. And S only has 1 area of space. Okay, so it's going to be 0. A P has 3 areas of space. So we'll either be in -1, 0, or +1. X, Y, Z. A D has 5 areas of space. So it's either going to be in -2, -1, 0, +1, or +2. Our F has 5 areas, -3, -2, -1, 0, +1, +2, +3. And G would have 9, so it would be -4, -3, -2, -1, 0, all the way across. Okay, so this is just telling me where the electron is in which one of these orbitals. That's all this is. And then MS is the spin. We can have +1/2, which means we have 1 electron in the orbital. Or we can have -1/2, which means the electron is paired. All right. So let's look at some of these and actually come up with their quantum numbers. Okay, let's start with oxygen. I don't know, I just picked that. And really what you need to do is you want its orbital notation and electron configuration. So oxygen has 8 electrons, its electron configuration is 1s2, 2s2, 2p4, 4, 5, 6, 7, 8. So let's go ahead and fill in its orbital notation. Up, down, up, down, up, 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 down. Now, when we're talking about coming up with the quantum numbers, okay, almost always we're talking about that last electron that we're adding. So this is the electron that we want to name our 4 quantum numbers. All right, so we're going to have 4 numbers describing this electron right here. This is my N, this is my L, this is my NL, my ML, and this is my MS. Okay, so here we go. Let's see if we can come up with our numbers. What principal energy level, because that's what N is this electron in? Well, it's in the second. Now, L, okay, L is telling us which orbital this is in. All right, now this isn't the correct way we number or label our p orbitals when we're talking about quantum numbers. Remember, if it's a p, it's -1, 0, or +1. So which one of these is that electron in? It would be in, oops, now I'm lying, we're getting ahead of ourselves. L is what sublevel we're in. We're in a p. Okay, so we're in a p orbital, so this is 1. Our ML tells us which one of these p's, which is our -1 number. Right? And then our MS is telling us our spin. 2 choices, +1/2 or -1/2, and it's dependent if it's paired or not. This is paired, so it would be -1/2. All right, let's try another one. Let's try, why don't we do, let's do magnesium. This electron it has 12 electrons. Okay, so it's 1s2, 2s2, 2p6, 3s2. So it's 2, 4, 6, 12 electrons. Okay, if we look at its this would be 1s, 2s, 3s, 2p, 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 3p, 3p, 3p. We don't need the d's. Okay, so let's go ahead and fill that in. Up, down, up, down, up, 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 down, 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 up, down. Now we want our 4 quantum numbers, and we're describing this electron right here, the last one that we put in. So this is N, this is L, this is ML, and this is MS. All right, let's start with N. N is the principal energy level, so this would be 3. L tells us what type of orbital we're in. Well, we're in an s orbital. Okay, so an s is 0. The ML tells me which orbital we're in. Well, an s only has 1 orbital. So this is also a 0. And then we have to know, is this paired or is it by itself? Well, this is paired again, so this would be -1/2. So these 4 quantum numbers are describing this electron right here. Now, the Pauli exclusion principle, and I didn't say this before, is just saying that there is no other electron in here that has these four exact same quantum numbers. None of them. Okay. All right. Let's try something a little bit harder. Let's try silicon. It has 14 electrons. And its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p2. Now, my question for you is, do I need to do this whole thing? I really don't need these core electrons. I really don't care about any of these when I'm coming up with my quantum numbers. I'm really only worried about this outside PEL. Okay, so I don't care about my core. So do I really need to write all this out? Well, not really. I just need to know this is my 3s, okay, my 3px, 3py, 3pz. And remember, this would be -1, 0, +1. So I would have an up and a down, and I would have an up and an up. So I'm looking to give my four quantum numbers for this one. Well, I need N, I need L, I need ML, and I need MS. Well, let's go ahead and do it then. So N is my third principal energy level, so it would be 3. L tells me we have a P. Okay, the quantum number for a P is 1. Now I need to know which P I'm in. Am I in the -1, the 0, or the +1? And in this case, I'm in the 0. Right? And now, is this paired or unpaired? And it's unpaired, so it would be +1/2. These would be my four quantum numbers for this guy. Okay? All right. Do we want to do another one? I think we're good. You're going to do some practice with this. Okay, so what I would do, when you're coming up with your four quantum numbers, I would have this little summary right here in front of you. Okay? Yeah, it'll be easier for you to come up with your numbers until you learn the different things. So as you're doing your coming up with those quantum numbers, okay, I would have this little thing in front of you. That will help you. Let's see, is there anything else I want to do? Yeah, the last thing I want to do, and it really doesn't have to do with quantum numbers, it's just kind of a cheat. Okay, so remember, that N is telling us the PEL. So there are some shortcuts. If I square N, it will tell me the number of orbitals in the PEL. Okay, so for example, let's say I'm in PEL number 1. So 1 squared is still 1. So that tells me that there's 1 orbital. It's one area of space. And you know that that first principal energy level only has an N. Well, what if I'm in the second PEL? Well, 2 squared is equal to 4. So there are 4 areas of space we find electrons. Well, we have an S, we have Px, Py, and PC. So there are 4 areas of space. So squaring n will tell you how many areas of space or how many orbitals there are. There's another quick shortcut. I don't know. If you square and multiply by 2, this actually gives you the number of electrons possible in the principal energy level. All right, so let's say we're in PEL number 1. How many can it hold? Well, if we use 2n squared, 1 squared is 1 times 2 is 2. It will hold 2 electrons. Now, we already know that the principal energy level holds 2 electrons, so whoop-de-doo. Well, what if we're in PEL number 2? Two squared is 4, times 2 is 8 electrons. The second principal energy level can hold 8. I'm only showing you this because you might get, there are multiple choice questions where it's asking for numbers of electrons and this kind of stuff, and you could just do a quick shortcut if you don't remember it. You know, I don't know if you're going to use that, all right, but I did want to show this to you just in case. All right, so that's all I have for today. Practice using your quantum numbers, and we were going to start going into light next class. All right, so have a good afternoon, and we'll see you soon.